All right, we have another function to talk about. And this time we're talking about the logarithm function. But I'm still going to use the same outline. Well, we could learn 100 functions and I would talk about every function the same way. You want to understand a function numerically. You want to know its domain and range. You want to know how it's graphed. Simplify is a pretty rare word in the world of functions, but changing it, rewriting logarithm functions, for example, is going to be a big deal. And then once you can do all that, you can cancel solve for x and even free the argument. All right. So the function I'm going to deal with on the numerical level is log base 2 of x. And when I say this, the logarithm function, it's a family of functions. It doesn't have to be log base 2. It could be log base anything. Each one would be considered a different function, I guess. But log base 2 of x is the function that I'm talking about here numerically. Now, with logarithm, you do have to be careful, and there are a few functions that work this way, where some numbers just work better than others. So the first one I did was log base 2 of 8. In other words, f of 8 would put an 8 in the argument here. And, well, we just know this. The exponent we put on 2 to get 8 is 3. Remember, that's what this is asking. 2 raised to what power is 8? And the answer is 3. So it's kind of asking the question, what exponent would we put on the base to get the argument? We've been over that. So I picked 7 here, and a little illustration here is saying log base 2 of 7 is a real number. It's an actual number. It's between 2 and 3. It's a little less than 3 because log base 2 of 8 was 3. So log base 2 of 7, a little bit less. But sometimes the best way to talk about an answer is just with the function, with the notation. In other words, if I want to talk about that point exactly, I don't mean a point next to it or close to it. I have to say log base 2 of 7. That's really the only way to talk about that point. But keep talking about doing this numerically. There are some numbers that do work numerically. 4. Log base 2 of 4. What exponent do I put on this 2 to get that 4? The answer is 2. I think this pattern is probably worth just pointing out. Log base 2 of 2. It's asking what exponent do I put on 2 to get itself. In other words, log base b of b. Well, the answer is 1 because the exponent I put on b to get b is 1. So numerically, don't forget fractions. Log base 2 of 1/2 is -1. Again, why? Because the exponent I'd put on 2 to get 1/2. We're asking what the exponent is. The exponent is -1. Domain and range. So let's write it down again. Y equals log base 2 of x. X is the set of values. That would not give an error in a calculator. And I'll just go ahead and write it out here. The domain is 0, infinity, or x is greater than 0. Not greater than or equal to 0. 0 doesn't work either, but x is greater than 0. So that's the domain of the logarithm function. Just the argument has to be positive, or the argument has to be greater than 0. And the range is a set of all possible y values a calculator might display. So let's go back to this numerical thing here, right? So we know I could put a fraction in, but I'd get an error if I put in a negative number. And basically the reason for that is if I put a negative number here, it would be like putting a negative number here. It would be like saying 2 to what power gives me, I don't know, -8, let's say. Well, there is no number I can raise 2 to get a negative number. Just doesn't work. You have a positive exponent or positive base. A negative number makes a fraction. 0 makes it 1. 2 to the 0 is 1. But I'm just not going to find anything that solves this. So basically what I'm saying is this has to be, the argument x has to be positive, but the answer can be negative. So back to that. The range, what is the range? Well, the range turns out to be negative infinity, infinity. And this gets reinforced by the graph. But like I said, the range can be negative. The answer for y can be negative. So negative infinity to infinity. Level 3 is the graph, but I say, you know what? First, let's talk about inverses. And this might not be required, but a lot of books do it this way. So I'm going to do it this way too. I'm going to talk about inverses. And I don't know, it's I guess you could see it as maybe a way of easing into the concept if we want to do that. Not a requirement, but first talking about inverses. All right. So I have these 2 partial tables here. And I think most people would agree that logarithm's a little cumbersome. So putting points on this table is harder, log base 2 of x, than it is to put points on this table, 2 to the x. In other words, if I'm plotting 2 to the x, I can just really pick any x value I want, and I can calculate it right away. In other words, 2 to the x. If I put in a negative 2, I'm talking about 2 to the negative 2. Hopefully you remember, 1/4. If I put in negative 1, it's 1/2. If I put in 0, 2 to the 0 is 1. If I put in 1, I get 2, 4, I get 9. All right. So just saying, you might not be that fast at it, but try it and run the calculation. I think it's pretty clear. But the point there is when you're plotting points and you pick your x values, they're easy to pick on this side. A little more difficult to pick your points with logarithm because not every number works really well. For example, we can't put negative numbers in here, right? So you remember all of that. So I'll give an example down here. I can put in, I'm just going to switch colors and it'll be obvious why I'm doing this in a second. We could put in 8, for example. And we just kind of went over this. Log base 2 of 8 is 3. And I see a typo here. That's pretty important for me to fix here. What was 2 to 3? I did that so quickly. It looks like I wrote 9. I think that was a 9. The correct answer is 8. Right? 2 times 2 times 2. All right. Why is that important? All right. Well, if we use this idea of inverse functions, I could actually use this blue table to populate this red table. And what I mean by that is this 3, 8 can be switched and become 8, 3. This 2, 4, 4, 2, 1, 2, 2, 1. And all of this is accurate, but it's a I don't know, trick that some authors use because my guess is they assume students just aren't all that ready to fill this table in directly. In other words, students wouldn't just come up with, oh yeah, let me put in 1/4 and calculate log base 2 of 1/4. Let me put in 1/2. And so they use this kind of bridging technique. How does it work and why does it work? Well, these are inverses of each other. So 2 to the x is the inverse of log base 2 of x. And if that's true, it means that if you have a point on one, you have an inverse point on the other graph. And I have that here. So this is why I wanted to talk about inverses real quick. The first graph has all of these points. And that's my image of the graph y equals 2 to the x. And I think not sure why that erased the wrong graph. I liked my graph actually. All right, let's try it again. Here's my graph going through those points. Y equals 2 to the x. And there's something about drawing that one first that makes drawing the logarithm graph a little easier. Not just the points. Now, I named this point A, and on the other page, I named this point A inverse. That A to the minus 1 means the inverse function. Well, if you see these points, for example, C was, let's put the ordered pair here, on the chart earlier was 0, 1. This point, 1, 0. X is 1, Y is 0. This point D was 1, 2, and this point D inverse is 2, 1. Now, what happens when you do inverse points and inverses is you get a function that's a mirror image of the other function. So these two functions are mirror images of each other if the mirror is this line y equals x. So the line y equals x is kind of where this thing reflects. Now, this is something I can never do in a regular class. I can't turn my whiteboard, the big whiteboard mounted on the wall, this way, but if I hold it this way where the line y equals x goes right down the middle of the screen, you can kind of see the symmetry that we talk about when we talk about a function and its inverse. So if you know a function's inverse, you have a clue as to what the function is going to look like when you graph it. Now, we could have done this directly. In other words, you could just understand logarithm numerically well enough to pick the values, calculate the points, plot those points, draw this shape, and left it at that. But sometimes inverse functions helps a little bit. All right, remember I said that the domain was x is greater than 0. Notice how for the red graph anyhow, I didn't use any x values like -1, -2. There's no logarithm graph here. Y equals log base 2 of x. And the range for y, you can see that y is negative. Look at the y-axis. There are negative values for y. There's positive values for y. So, yeah, the range is -infinity to infinity. I don't know. I think that domain and range are finally getting interesting. And a lot of times, like a function like, I don't know, square root. Well, square root's kind of interesting, but a lot of times the domain and range are the same or something, but, there's a difference here. All right. Manipulating logarithms. Let's look at these. I just wrote these down. Of course, these are in the on the website certainly, but you can manipulate a logarithm. The direction you manipulate a logarithm isn't really really isn't one particular direction. In other words, there's not a way to simplify. We don't simplify logarithms, but sometimes we'd rather have two separate logarithms instead of and sometimes we'd rather have one logarithm. So here's an example of logarithm formula. But the point is, it works in both directions. Sometimes you want to take this side, make it this side, or this side, make it that side. But notice what happened. This was a multiplication, and over on this side, it's an addition. Quirk that's specific to logarithms. So kind of similar idea, log of a division becomes a subtraction of the two separate logarithms. This one is another one. Let me make it clear where the argument is. Log base b of m raised to the r. I can change that to r times. And that's a little, get rid of that. Okay. R times log base b of m. So it's like this r. This r came around and came out front. And it's a really powerful thing because it does free an argument sometimes. So we might need to use that later. We've already talked about well, so let me just go ahead and complete this problem here. So this problem here is saying, well, I can write it as log base 3 of x times y. This one's going to take a couple of steps. I can write this as log base 5 of x squared plus log base 5 of y to the 4th. And hopefully you see what I'm doing here. I took this 2 and brought it up into the argument. Took this 4, brought it up into the argument. Now that I have this, I can put it all together. Log base 5 of x squared y to the 4th. So this would be a good manipulation if they asked me to write it as one logarithm. Now we've already talked about logarithms like this, problems like this. This is one of those problems I'm not really sure where it falls. I mean, it really is a numerical question, but because of calculators, the way they are, you have to manipulate certain problems with most calculators. So I can change this log base 4 of 8 into log base, well, any base, 10 of 8 or something else. I'm going to use 2. If I do that, log base 2 of 8, remember, has an answer. Log base 2 of 4 has an answer. I get 3 over 2 or 1.5. Now that's the same answer you'd get if you ran this through a calculator. The way we learned how to do it earlier, log of the argument divided by log of the base. And if I ran it through a calculator this way, by default, I'm using base 10. And the way I wrote this here and the way this is written here are really just division. It's just that this is the way we typically do it if we're doing it by hand, in algebra class. And this is the way we might do it if we're doing it on a calculator. And the point is, even on a calculator, you get the same result. All right, well, I don't want this video to get too long that I can't upload it or it takes too long to upload. So I'm going to do level 5, solving for x, in another video. But what I've talked about so far is, let's go all the way back to the top, understanding logarithm on 4 levels. Sorry, scrolling through this. Okay. Numerical, domain and range, graph, and manipulating and rewriting. So we'll do this one in our next video.